So, so the next talk is by John Granzow with a bunch of people that Tiffany, Chris Chafe, and Romain Michon. And the title of the talk is Mending Bells and Closing Belfries with Faust. What are Belfries? Belfries? Ah, d'accord. Why it's Belfries and not Belfries? Oui, oui, non, c'est la prononciation, mais bon. It's English, okay. Forget about these details, sorry.
Yes, thank you, Alfred and Graham, for organizing this conference, first of many. I'm going to help us catch up. We used Faust to resynthesize the Tsar Bell. Any questions? Now we're caught up. No, this is an interesting project that includes many people, not only the authors. Tiffany Ng is the Carillonist at the University of Michigan, where I've been working for 3 years. She arrived when I arrived, and I was so delighted when she was so willing to experiment with speaker arrays in the towers, in the Carillon towers, for electroacoustic experiments and for developing the Carillon repertoire. And so I'm going to talk to you a little bit about a class that's been doing these kinds of things, a performance systems course at the University of Michigan, where we use contemporary technologies for music, and we also interface with existing instruments. And what more interesting instrument than the Carillon? This led to a Resonance and Remembrance Symposium, an interdisciplinary bell studies symposium at the university. And in parallel, we were working with Chris Chafe and Greg Niemeyer and an entire team to try to resynthesize the Tsar Bell, which is the largest bell in the world, which sadly, although maybe fortunately, broke because it provokes this interesting question for sound synthesis. What did that bell potentially sound like? So I'm going to talk about the context of these things. When I arrived at Michigan, I immediately perceived the resource of the bells. 2 grand carillons. Grand carillons have 5 octaves. There's actually only 23 grand carillons in the world, 2 of which are at the University of Michigan. Lurie Tower sits in the middle of the engineering school, and Burton Tower across the river on Central Campus, each having up to 60 bells and at once time-keeping architectures and a musical instrument and offices. So students get to compose pieces for these instruments and experiment with speaker arrays in the tower projecting onto the campus. It's an instrument that plays to the zip code, as we say. Oh, I didn't put the audio in. For those of you who maybe haven't... A strictly mechanical instrument with springs for mechanical advantage. When played acoustically, there's no motors or electronics involved, and there's all kinds of interesting delays with the sound projected onto the city below. Well, the first thing we did was to see if our speaker array was sufficient to match the amplitude of the bells. This recording may not sound that interesting, but it was a spectacular moment for us when we realized that with our Electro Voice array, we could match the amplitude, at least for one perspective, for listeners right below the tower. So the first bell sound here is the sample recorded from the Sather Tower at Berkeley, played from the speakers, and then I tried to find the same note on the real Carillon, and this is recorded from the ground. So this was the moment where we realized this could be done with our speaker. That's a sample. I missed it by 1 semitone. But at least this was a proof of concept that we could have an audience in a certain spot, and we could do electroacoustic music, live processing the bells, have students bring up their controllers and compose with students in Tiffany Ing's Carillon studio. It was hard for me with all the work I was doing setting things up and teaching to get good documentation. This is one of my favorite, nonetheless, one of my favorite little snippets of a piece by Rebecca Fisher and Alex Miller called R.C. Carillon, where they live processed the bells. There's microphone arrays within the belfry and transformed the tails into shepherd's tones using Max MSP in this case. Have a lot of fun with noon-hour concerts where this iconic instrument suddenly becomes very strange. Although one of the criteria of the assignment is to try to retain somewhat the character of the instrument to draw this kind of attention of the instrument transforming. In parallel, Greg Niemeyer at Berkeley was asking the question, what are the latest tools to create an educated guess as to the sound of the Tsar Colloquial 3 Bell, which is in a third generation Tsar Bell that shattered or cracked during its casting when a fire happened at the Kremlin and they doused it with water and there was a thermal shock and an 11-ton chunk fell out of the bell, which is about the weight of the biggest bell in the Charles Barrett Carillon. This bell together would weigh over 200,000 kilograms. And so it's become kind of an icon of imagined sound. What would this bell have sounded like? And it's not a new technique, but obviously one of the low-hanging fruit is a structural analysis or a finite element analysis of the bell, which Romain talked about a little earlier. So this was cast in 1735. We just thought, well, let's just verify that FEA gives us a good representation of the modes. We had a little dinner bell that we modeled in SolidWorks and did a finite element analysis. That's the real bell. So at least in this case, we have a ground truth. And resynthesized in this case in Chuck, which is a programming language I often teach with. And we see that there was some fidelity there. Whether that will translate to a 200,000 kilogram bell is another question. We did all kinds of research with Oya Dubitova was the only Russian-born artist on the team, digging up all kinds of profiles of the Tsar Bell. There is some advantage to the fact that it's broken and that we can see the profile. And if I had ever gone there, we could maybe measure it. But we were relying on resources online and these kinds of diagrams of typical Russian church bell profiles. Once the profile was acquired, it was swept around its center axis as an extrusion, and bronze was selected for the finite element analysis with the different variables required for that analysis, the elastic moduli and density. The future of this project, of course, is to use Faust to mesh. At the time we were doing this, Romain had yet to finish it. Now, of course, we would do that and actually probably get better results. With SolidWorks, although we did have these nice animations, initial drawings included the crown. The final simulation did not include the crown. But this gives us the exaggeration of the overall displacement of the fundamental frequency, which we found in this analysis to be about 49 hertz. Not necessarily the pitch you hear in a bell, as that is the hum tone. The strike tone will often be an octave above, which is the perceptual pitch of the bell. Initial simulations, obviously you're going to miss the low frequency of this, but our initial simulation sounded very much like a gong. And so the rest of the resynthesis was very much ear-driven as we looked at the typical spectral features of Russian church bells and adjusted some of the decay rates. Because of course FEA does not give us the decay rates of the modes, and that was a big problem for faithful reproduction. It does? Okay. Well, the future, yes, bye-bye. So these are, we used a subset of the 1,000 partials that SolidWorks gave us. You'll notice a lot of very similar modes. These are the doublets you often get with symmetrical resonators that account for the warbling, wonderful warbling sound you get with bells. Chris Chafe implemented this as a bank of biquad filters in Faust, and we was excited by a noise generator with a sharp envelope triggered when the input of the system exceeds a set threshold. So we wanted to, in the iteration at Michigan, we wanted to integrate the Tsar Bell into the instrument. We wanted Tiffany to be able to actually excite that virtual model with the Carillon keyboard. So we had an envelope follower that captured the vibration of a clapper on the largest bell, and when it exceeded a threshold, they would play synchronously because we found that they actually mixed quite nicely. So there is your typical block diagram of this resynthesis using biquad filters. And we had two concerts in April of 2016 and October of 2017, both of them with Carillons, the first one at Berkeley at the Sather Tower, and the second one at Michigan at the Burton Tower. These were very different concerts, and I'll show you how they were set up. Belfries closed today. Some somewhat calamitous political events happened in between these two concerts, and we became very aware of maybe the moment of projecting a Russian bell from a Carillon in Michigan had a certain import at that moment. And so we had this Belfries closed today poster. At the Berkeley Tower, the installation was a scaffolding donated by Meyer Sound that was separate from the tower, 12 subwoofers suspended from a custom scaffolding. And you could trigger that bell from your patch being played up in the belfry, but there was all kinds of delays and that were hard to sort of figure out, and the audience had very peculiar issues of where to listen to this concert. There's a image of the distance between the two setups. At Michigan, we decided to integrate the low bell into the Carillon with another donation from Meyer Sound, two full-range opera house speakers. This is interesting generally in that every 5 semitones it takes, you have to double the amount of metal to go lower. So it's a very expensive instrument to extend in that respect. And so this is an interesting application for that. Two of the composers that submitted works that we know well, Chris Chafe and Christopher Burns. You have to be careful when you volunteer for these things, you end up hanging rigging for the concert itself. The clapper was ideal to capture the impulse, to trigger the model, because of course it's a highly damped structure, 300 kilograms, and we could, Tiffany could very accurately decide whether to only play the Baird bell or to find the fortissimo that would activate also the Tsar Bell. So this is maybe a little bit of listening. Christopher Burns' score note is interesting to read, and you can hear that within his piece there's a very low note which is synthesized to Tsar Bell. And of course we're missing the low end, but it's and this is the Faust for Live implementation. I should be able to. Yes, I can trigger it now with my microphone. That microphone was the transducer on the clapper. So we're hearing as low as we can go with the system here, but that was our attempt to integrate a very low bell into Carillon repertoire at Berkeley and Michigan. Thank you. I'd like to thank the rest of the team, as well as Graham. Any questions?
Any question?
I don't imagine that there are a lot of recordings of the actual Tsar Bell being struck, such as it's broken and it's resting muted on a concrete platform.
Did I forget to say that? It's never been struck.
Yeah. But so you made one physical model of a small bell to compare to your real recording of a small bell. Did you scale up that test during the process to try and compare your physical model of a really large bell to one of the ones in your Carillon?
No, we didn't, although there was rivaling models. One of them was actually just scaling measurements from existing Russian church bells. And so Richard Strauss was very involved in that and helped us with our model as well. So this was not really an attempt to say we have found the sound of the bell. It was to participate in this ongoing imaginary of what are our tools to make a guess. But yeah, that would be a good thing to do, to actually acquire. We don't have any of those bells to play with, but if anyone has.
I have one question, but it's also for you. If you do the Faust to mesh version of that, would that sound exactly identical to the current model, or?
Romain, you just told me that Faust to mesh would be better. Of course you say that.
So what's very tricky with Bell modeling is that the T60 of all the modes is so long, and it has a really significant impact on how the whole thing sounds. So like in a violin body, T60s are very short, so they don't play a big role. But in the case of bells, like the lowest mode can resonate for like 40 seconds, and so Mesh to Faust now implements a damping matrix, and so it can compute the T60 or estimate the T60 other modes. So you would definitely get much better results than what you got from SolidWorks, where you only get the frequency and the gain of the modes. But one thing that I wanted to add is that bells are really tricky, and that was kind of to follow up on Michael's question. Like what's very hard with bells is especially if they are very big like that, is the amount of material that you have to displace, basically. And if you have a tiny bell, then just scaling the bell is not necessarily going to sound the same than if you had a tiny bell, because with a tiny bell, when the clapper hits the bell, then the whole piece of metal is going to vibrate. Well, if you have a very large bell, most of the time the clappers that are in very large bells don't displace the material the same way that it would happen in a small bell, because it's so big. And especially in the case of Carillons, the clapper is basically placed right next to the bell, so that if a human presses the key on the keyboard to push the bell, there's enough force mechanically to strike the bell. So there is only like that very tiny distance to do it, and of course the bell is going to sound completely different if you just like strike it ding like this, than if you have like 5 tones clapper just like striking the bell, right? And so yeah.
So, when you model them, you model also this part? No.
No, because well, you make a model of the bell, and then you run finite element analysis on it. But like we just assume that. The way you drive the bell is just by sending a signal to the system, at a specific.
Yeah, much more to do with modeling.
Yeah, at a specific point, and
radiation pattern.
And I mean, like the way I think the way John did it here and the way we do it in general is pretty dirty in a way, because in the end it's just it's like a noise generator with some kind of envelope on it, and in theory it should be much more than that, because the coupling between the clapper and the bell when the clapper strikes the bell is more subtle than just this, but and definitely plays a very, very, very important role in how you perceive the sound. So yeah,
Much more work to do.
Thank you. I have just a little question about the where do you put the capture the sound, the microphone position? Because I guess the radiation pattern of such instrument is important, no? Like where you capture synthesize the sound? At what special location? I mean, around
Yeah,
the
we didn't do that.
So, but like you have this radiation model, and then
it's a model, physical model, right? So so the way it works in this case is that the like it's just like if you're listening to all the modes at the same time, right?
Okay.
And, so it's like if you put an infinite number of microphones around the bell, you know, like,
Right.
All right.
You're not. And bells are so tricky to model also because of that, because very often they interact with the belfry, and then you have all these resonances from the belfry itself, and also from the wind and all these things, you know, that completely change the way you perceive the sound of the bell from the ground. Like, I mean, I remember, like, for the symposium that John organized, I made a lot of bell models using all this, you know. And I worked so hard on this, you know, and I was sitting on a cafe in this village in France, you know, and then the bell started ringing, you know, and then I was like, it really doesn't sound the same as what I'm doing.
Yeah.
Like, it's because of that, probably.
Okay, so thank you very much, John.